Today we are going to study on the topic of aromaticity. First, let us take this compound cyclohexene. If I add bromine to this, what I get is dibromo compound. Okay, let us go for another compound like this, diene. If I add bromine, depending on the condition, I will get two products. Like this, or like this. So this is thermodynamic product, this is kinetic product. At high temperature, we will get this. I go for triene and I add bromine to this. The product, what I expect is like this, a dibromide. But this product will not be formed. Instead of that, I get bromobenzene. The first two examples, two bromine atoms are introduced into a molecule. But in the case of benzene, we get only one bromine atom. What is the reason? There is some property in benzene which doesn't prefer the regular reaction pathway. What is that property? It is nothing but aromatic character for benzene ring. This aromaticity can be explained based on Huckels' rule. A molecule is aromatic if it is cyclic, planar, there is extended conjugation, the last one, the number of electrons involved in extended conjugation is 4n plus 2. If all these four are fulfilled, satisfied, then that compound is aromatic. A compound is anti-aromatic if it is cyclic, planar, there is extended conjugation, and the number of electrons involved in extended conjugation is multiples of 4, then it is anti-aromatic. So the difference between aromatic and anti-aromatic is only the number of electrons. In anti-aromatic, it is 4n number of electrons. In aromatic compounds, it is 4n plus 2 number of electrons, where n may be 0, 1, 2, goes like that. There is another type of compound that is nothing but non-aromatic. A compound is said to be non-aromatic if any of the following three condition is not satisfied. That is, the molecule, if the molecule is not cyclic, then that is non-aromatic. If it is not planar, then also we say they are non-aromatic. If there is no extended conjugation, then also it is non-aromatic. So first try to find out whether it is aromatic or anti-aromatic. If it doesn't fit into these two categories, then you can say they are non-aromatic. Here, it should not be cyclic, should not be planar, there should not be extended conjugation. Even if one condition is not matching, then immediately you can say it is non-aromatic. I make it into a table. Now we are going to discuss on the stability of aromatic compounds. Aromatic compounds, they are highly stable. After that, we have non-aromatic compounds. Then anti-aromatic. This is energy increases like this. Aromatic compounds have less energy and more stable. Anti-aromatic compounds, they have high energy and they are less stable. This one, it is very important because this decides the chemical property, physical property of a compound. An aromatic compound, since it is more stable, it may not prefer to become anti-aromatic or non-aromatic, which have higher energy and less stability. On the other hand, anti-aromatic compounds and non-aromatic compounds, they try to become aromatic compounds. If there is any possibility for the anti-aromatic compound or non-aromatic compound to become aromatic, then that reaction will be very facile. The reason is the stability of aromatic compound is very high. So it prefers to be in the most stable form. Now let us try to understand the 4 criteria that has to be fulfilled for a molecule to be aromatic. The first one, the molecule should be cyclic. Generally, the compound, whatever they give in the problem, will be cyclic. They don't compare a triene like this and benzene. So this cyclic easily you can identify, so there won't be much difficulty. What about this compound? Styrene. Here you have to consider only the cyclic portion. The number of electrons, it is 4n. There are totally 8 electrons. But when you go for aromaticity, you have to consider only the cyclic part. If the compound is something like this, if a bond is formed between this and this, you may get this. I don't know whether this compound exists or not, whether it is available or not. But now, the whole system, it is cyclic. You have to consider this double bond also. So the number of electrons, it is same. But this compound, this cyclic portion, it is aromatic. This one, it is anti-aromatic. because in this we didn't consider this double bond since it was in side chain. In this case it is in the ring, so we have to consider this. The second criteria, it is planarity. To understand this, I go for the structure of benzene. So this is benzene. All the pi orbitals are overlap like this. Because of this overlapping, it becomes more stable. The overlapping of this p orbital is possible only if all the carbons were in the same plane. If the planarity is missing, then this kind of overlapping is not possible. It is not compulsory that all the carbons should be in the same plane. Sometimes all the carbons may not be in the same plane, but they will be planar enough to overlap with the neighboring carbon p orbital. This overlapping of p orbital gives extra stability to the system. That extra stability is known as resonance energy. How to find out whether a molecule is planar or not? It is very simple. Try to follow this. Up to 7-membered ring, the compounds, they are planar. It may be a system like this or like this. Up to 7-membered ring, there is no question about planarity, whether it is planar or not. Without thinking much, you can consider them as planar. When you go for 8-member, the annulenes, basically they are cyclic polyenes. Let us consider this molecule. Cyclooctatetraene. The number of electrons in this is 4n. So it should be anti-aromatic. Provided if it is a planar molecule. If the planarity is not there, then this molecule will become non-aromatic. You may know that non-aromatic compound is more stable than anti-aromatic compound. For this reason, this molecule doesn't exist in a plane. So it prefers to exist like this. A tub shape. Now we can see here the pi orbitals cannot overlap effectively. The distance between this and this, it increases. So the bonding interaction will be very less. They cannot overlap. On the other hand, if I add 2 electrons to this, what I get is a molecule like this. Now it is 4n plus 2 system. The number of electrons, it is 10. So this should be aromatic provided if this molecule is planar. So this particular system becomes planar when you add 2 electrons because it is aromatic. For the same reason, 12 aniline, 16 anilines, in which the number of pi electrons are multiples of 4, they are non-planar. And there is no question about anti-aromaticity. It cannot be anti-aromatic. So 12 aniline and 16 aniline, even 8 aniline, they are non-aromatic. They can twist themselves to become non-planar. On the other hand, when you add 2 electrons or when you remove 2 electrons from that, the same system becomes planar and it attains aromaticity. Here, I go for a system like this. The number of carbon, the number of pi electron, it is 8. So it is 8 electron system. Since it is bicyclic compound, it cannot freely rotate and it cannot change its structure. So it becomes planar. It is cyclic, it is planar. The number of electron involved in the delocalization, it is multiples of 4. So this compound, it is anti-aromatic. This compound name is pentylene. If you add 2 electrons to this, then that will become aromatic. That's why if you add base to this proton as well as this proton will be removed easily to form this aromatic compound. This one, it is non-aromatic because there is no extended conjugation, but this is aromatic. The number of pi electrons, it is 10. So this becomes aromatic. So these 2 hydrogens are highly acidic. Now let us go to the system which has 10 pi electron. The most common system is naphthalene. It is polyaromatic hydrocarbon. There are 2 6-membered rings. If I break this bond, then what we get? Consider like this. In this olefins, they are Z olefin, and these 2 olefins are E olefin. When you look at this molecule, it looks like it is a planar molecule, but in actual it is not planar molecule. The reason is this hydrogen and this hydrogen, they are very close. Because of that, there will be repulsion, steric repulsion between the two hydrogen atom, and the planarity is lost. Because of that reason, it is not planar. So it is non-aromatic. If I connect this, by a methylene group like this, then what will happen? This compound is aromatic. Is it possible for this molecule to be a plane? All these 10 carbon atoms should lie in the same plane. It is not possible. They are not in the same plane, but they are planar enough to undergo efficient overlapping of pi orbital. So it is not compulsory that all the carbon atoms should be exactly in the same plane. If there is planarity sufficient enough for pi orbital overlapping, that's okay. That is available in this. So this behaves like aromatic compound. Instead of this methylene, I can introduce oxygen atom also, or sulfur, NH, NR, PH. So it goes like that. Basically, this kind of compounds, even though it is not exactly planar, they are aromatic. Another well-known system is azulene. The number of electrons in this, it is 4n plus 2, 10 electrons are there, and it is cyclic, it is planar, there is extended conjugation. So it is aromatic. This can be easily explained based on this structure. If you see this, you can find trophyllium cation and cyclopentadienyl anion. Both are aromatic in nature. So this has high dipole moment. The reason is we have charges plus and minus. Because of this polarization, this ring becomes cyclopentadienyl anion, which is aromatic, and this ring becomes trophyllium cation, which is again aromatic. That is the reason why this azulene exists in ionic form. It has high dipole moment. It may be soluble in water to some extent, whereas naphthalene is completely insoluble. But this azulene, it is soluble in water to some extent. I can go for another resonance structure also, it may be very clear. So this one is trophyllium cation, and this part it is cyclopentadienyl anion. I have another interesting system It is like this. Something like this. Is this molecule aromatic or not? First of all, this carbon, it is sp3 carbon, so it should be tetrahedral in shape. In such case, will it be aromatic? So it is cyclic, but planarity is not there because of this tetrahedral carbon. What about the number of pi electrons? There are 10 pi electrons, so it is satisfying Huckel's rule of 4n plus 2 number of electrons. Even though there is no planarity, the planarity is sufficient for pi overlapping. So this behaves as aromatic compound. When you add a base to this, then what happens is the base abstracts this proton to generate carbanion, and what we get is this carbanion. Now this carbon becomes planar. So this is more planar compared to this. But what about the number of electrons? The number of electrons present in this anion is 4n electron. So there are 12 electrons. So is it anti-aromatic? No, it is not anti-aromatic. Only these peripheral pi electrons involved in overlapping. This one will not participate in overlapping, so it will remain as such. So only these 10 electrons involved in pi orbital overlapping. So the electrons, number of electrons involved will be 4n plus 2, that is 10 electrons. And it is more aromatic compared to this because it is more planar than this. I go for higher annuline. So it is 14 annuline. The number of pi electrons will be 4n plus 2, 12 plus 2. Even though the ring size is very big, in order to attain aromaticity, this molecule will be in a plane. So basically it is planar molecule. Not only 14 annuline, even 18 annuline, it will be planar. Another interesting compound will be this one. It is modification of that compound, earlier compound. These hydrogens has been connected by a carbon. Now, what about the planarity? This carbon, it is sp3, so it should not be in a plane, but it is planar enough to have pi orbital overlapping, and it becomes aromatic. Another interesting example is this compound. Instead of this 2 methyl group, I have double bond. What about this? The number of electrons, the number of pi electrons, if you count, it will be 16. Is it anti-aromatic? No. If the benzene rings are there, then you should not count like this. These compounds will come under polyaromatic hydrocarbons. So, naphthalene, chrysaline. So all these compounds will come under polyaromatic hydrocarbons. Even though the number of pi electrons present in that it is 16, it is not anti-aromatic. It is aromatic in nature. Look at the system. It is 16 aniline. 16 aniline, the number of electron, it is multiple of 4. So it is expected to be anti-aromatic, but it is not planar. So it is non-aromatic compound. But when you add 2 electrons to this becomes planar and it becomes aromatic. The same way, if you remove 2 electrons from this, then also it becomes planar and aromatic. So the aromatic property, the aromaticity design criteria, the structure of this extended conjugation. What I mean by this extended conjugation? Let us take benzene. I make this bond somewhat thick. This is the another resonance structure. The thick bond is here now. Then further I can go like this. In that the thick bond will be here. I can go like this, and if I compare all the resonance structures, this thick bond will delocalize on all the carbon atoms. So that is called extended conjugation. That is not possible if there is any sp3 carbon in the ring. For example, this carbon, it is sp3. This also it is sp3. Not only because of this carbon, you can even compare. The extended conjugation is not possible. The plus charge can fall here. Take this cation, cyclopentadienyl cation, indicate like this. In this, that's all. If you draw the resonance structure, you will get plus charge here. Then here, further on this carbon, so now the plus charge is present on all the carbon atoms. You can see that very clearly here. So on all the carbon atoms you can find the plus charge. So not only delocalization of double bond, you can compare this positive charge also. Similarly, you can go for minus charge. If you draw the resonance structure, this minus charge will be on all the carbon atoms. That's why we write like this. One more thing. Lone pair of electron. This lone pair of electron also can involve in extended conjugation. But when it involves in extended conjugation, what you get is a localized positive charge and a minus charge which can be delocalized on all the other carbon atoms. So that also is possible. Now it is similar to cyclopentadienyl anion. The last criteria is number of pi electrons involved in delocalization. Let us go for some example. First one, compound which has only double bond. There is no problem at all. What is the number of double bond? Multiply by 2. So it will be very easy. If there is any positive charge on the molecule, it will not contribute to pi electron. You have to consider only the double bond. So here there are 3 double bonds. There are only 6 pi electrons. If there is any minus charge, then the minus charge will contribute 2 pi electrons. So here there are 6 pi electrons, 4 from the double bond and 2 from this minus charge. If there is heteroatom with lone pair of electron, it may be nitrogen, sulfur, oxygen, phosphorus, selenium. All these atoms have lone pair of electron. So they can contribute 2 electrons for the molecule to attain aromaticity. So this lone pair of electron is equal to 2 electrons. So here we have 2 double bonds. So it accounts for 4 electron plus 2 more electron on nitrogen. So total there are 6 electrons. Interesting thing is comparison between this molecule. First one, it is pyrrole. I mentioned the lone pair on nitrogen gives 2 electron for the molecule, so it becomes aromatic. What about this pyridine? Already there are 6 electrons. There are 3 double bonds, so there are 6 electrons and 2 more electrons from nitrogen. So the total should be 8. That means, is it anti-aromatic? No, it is not anti-aromatic. The nitrogen on the pyridine will not give 2 electrons. The reason is this is the structure of pyridine. The lone pair of electron is here. The pi electrons are like this. So the lone pair is in an orbital which is perpendicular to the pi orbitals. So this cannot involve in overlapping with this. So it cannot contribute. In simple sense, I can say if there is a system like this, if there is no hydrogen or methyl group or alkyl group attached to the nitrogen, that nitrogen cannot contribute to aromaticity. That nitrogen cannot contribute electron, lone pair of electron to the molecule. I can go for several examples like that. So this is imidazole. This will give two electrons, that is lone pair of electron. Even though this nitrogen has lone pair of electron, that will not participate in the overlapping. I can go for pyrazole. Here also the same thing. This nitrogen lone pair will not involve. I can go for this compound also. There are two nitrogens and there are two lone pairs. It will not contribute. Only when there is NH or N alkyl group, that will contribute. In the other hydrocyclic compounds like thiophene, this lone pair of electron can be given to the compound. Similarly, this one. Even though there are two lone pair of electron, only one will be given for aromaticity. What about the aromaticity of hydrocyclic compounds? Most of the hydrocyclic compounds, what we generally come across, are aromatic in nature. For example, let us start with pyrrole. The number of electrons involved in the delocalization is 6. So this is aromatic. What about this one? Already there are 6 pi electrons. In addition to that, there is a lone pair of electron. So the total number of electrons, it should be 8. Is it anti-aromatic? No. This is also aromatic. The reason is this lone pair of electron is in the orbital which is perpendicular to the pi bonding orbital. So this lone pair cannot overlap with this one. Only these electrons involved in delocalization and only 6 are there. So it is aromatic. Easily you can remember if there is a system like this. Double bond N and there is a ring and conjugation is there. Then this lone pair of electron will not involve in delocalization. You can go for system like this. This lone pair of electron will involve in delocalization. On the other hand, this lone pair of electron will not, because it is like this. Not only nitrogen, you can take oxygen also, furan. Similar to nitrogen, this also can give lone pair of electron. There are 2 lone pairs of electron, but only one will involve in delocalization. So it will be 6 and it will be aromatic. Here is an interesting problem, that is furan and pyrrole. If you treat this with a dienophile, let's go for maleic anhydride. Furan will react with this to give the addition product, Diels order addition product. But pyrrole will not give. What is the reason? Both are aromatic. So when it undergoes Diels order reaction, this aromatic compound becomes non-aromatic. Then, what is the driving force for this reaction? Why it takes place? On the other hand, pyrrole doesn't react. What is the reason? Another type of compound is fulvene and fulvalene. So this kind of compounds are called fulvalene. A conjugated polyene is connected to exocyclic double bond. The same thing if you attach another ring that is called fulvene. What about this? The same compound if it exists like this, then this ring becomes aromatic. So this is the driving force for this molecule to exist partially ionic. It is not completely ionic, but there is some ionic character for this. Because of this, the dipole moment and polarity will be high. If you consider this molecule, the dipole moment will be very low. But when you go for this one, the dipole moment will be very high. If this molecule exists like this, then the dipole moment should be very less. If you consider this ionic form, then the dipole moment should be very high. Similarly, polarity also should be very high. It has been observed that the dipole moment of this compound is higher than the calculated for this because of this structure. I can go for one more, fulvalene.